So my name is Sri Krishna, and I'm part of Dassault's worldwide enablement team for simulation. And I'd like to welcome all of you to this session. It's a pretty long title, but the core of this session will focus on how can you leverage combination of design and simulation to make your products stronger, smarter, more comfortable if comfort is a requirement, and smarter. And during this entire session, we'll first take a look at this example that I'm going to use. It's a excavator that we designed at Dassault to go through the pains that our customer would actually go through and leverage simulation to address some of those pains. I'm sure you might be hearing the term 3D experience works a million times today. But before we jump into the solution, I just wanted to highlight some of the key business drivers that the industry is experiencing over due time. First and foremost, enterprise agility. We've all seen through COVID how important it is for everybody to stay connected, work virtually, and we made it work. Right? There's no doubt that's okay, that's doable. Equipment as a service, I heard a couple of you mention that you develop business-to-business solutions. So I presume that's another key trend as well as a challenge. Enterprise risk planning is something that we're seeing quite often. Production of one, so a lot of customization requirements are coming in from customers. So we are going from mass production to mass customization. And last but not the least, the circular economy, circular innovation that everybody's talking about. So these are some of the trends that we notice in the industry, the key business drivers, but they also introduce a lot of challenges, right? Product failures on the field is quite common. And every day we're trying to reduce the number of failures for multiple reasons, not only to improve the quality of the product, but also to maintain the image of the brand, right? The mind share of the customers. Then you have the prototyping, which I'm sure you would agree is a pretty big, sizable portion of the cost, right? Where you're building physical tests to replicate what happens on the field, and that takes a lot of time and money. In product variants, which has increased quite significantly. For example, all of you may have heard of this customer of SolidWorks called Resimin, right? They make mining equipment that does a lot of drilling activities underground. And their biggest challenge is that each customer has their own requirement for the drilling arm. So they need to come up with something like 10 to 12 variants in 3 months. And typically in the past, they would design 3 full machines in 1 year. But now being able to leverage combination of design and simulation, they have gone from 3 equipments to 125 equipments in a year. Right? So they are able to offer this customization to their customers. And last but not the least, shortage of skilled labor. You're starting to see a pattern where you have less number of people doing more number of jobs or wearing more number of hats. So mechanical designers this day are not the same as mechanical designers 20 years ago, where we had specific compartments, right? We had the designers, the analysts, people who manage data. But if you're working for an industrial equipment company, you're probably a one-man shop, doing a little bit of design, a little bit of supply chain, a little bit of manufacturing, and some simulation, right? So these are the trends we looked at. And we're like, okay, if we were to put ourselves in the shoes of the customer, how do we address these challenges? So we created this model called B-Excavator. And we thought, okay, the typical challenges that are experienced by a customer from a product failure standpoint is in terms of safety and durability, where either you want to increase the strength of the product and in some cases, increase the life. And comfort is big. Human comfort is becoming a major requirement, especially if you're into equipment that involves an operator, right? Having the operator experience thermally comfortable atmosphere is a key requirement from a lot of the customers. So that's another requirement. And then Internet of Things and 5G. So you're seeing that, for example, we were talking to Resumen and few other customers. They are placing these antennas on their heavy machinery so that they can track the movements, so that they can map and study the history of the movements, and also ensure that they have the most optimal operations. So in order to address these requirements, which are enhancing the durability, safer protection for the operator, and then thermally comfortable cabins, and doesn't have to be cabin. I mean, if you're designing anything to do with human interaction, safety plays a key role. And last but not the least, intelligent systems, which is including antennas, design of communication systems. So um, let's talk about ModSim approach first. And what do we mean by ModSim? And then we jump into each of these requirements, and I'll show you how those could be addressed. So in very simple terms, you've been hearing the term 3D Experience Works. It's a portfolio of solutions that are offered on an integrated platform called 3D Experience across design, simulation, manufacturing, governance, and marketing. These are all the DS technologies put in one single cloud platform. Right? That's the simplest definition of 3D Experience Works. But what we want to talk about today is this approach called unified modeling and simulation, where your design is so closely tied to your simulation that you can very quickly make iterations, design changes, and simulate all kinds of physical scenarios to improve the product performance, to address the key requirements we talked about. So at the heart of the ModSim approach is actually requirements. So you can actually capture the requirements in your feature tree. So just like you have your feature tree in SolidWorks, the feature tree on 3D Experience platform can actually capture requirements, high level requirements, and you can tie them to the actual features. For example, if there's a requirement to increase thickness of a particular part of the boom, when you do increase the thickness, you can actually tie that feature, that extrude, to the original requirement and ask if I have passed this requirement check or not, right? So it starts with requirements. So first is the very high level requirements, which is enhancing the durability and strength, improving the safety, and we also have an operator seat that's involved. This is a good example for supply chain, where if you have a tier 1, tier 2 supplier who's supplying a particular part or product, then that could also be considered. And then intelligent machinery for operating system. So these are our requirements that we're going to start with. There's a collaborative aspect to it, which I love about the platform. I'm a hardcore SolidWorks user myself. I was certified CSWE 9 years ago. I got my Elite Applications Engineer Award when I was working for a reseller. So I'm a huge fan of SolidWorks. What I felt was missing was some of the collaborative tools where you can very easily communicate. Yes, we were using DraftSight to a certain degree. We were using e-drawings, PDM to a certain degree. But this stuff is really, really cool as to how you can have communities, how you can have posts and instant messages between the same group tied to a particular design. So it's not like social media, it's more specific to a design, to a project, right? So, and all this are still tied to your requirements. And then comes the fun part, which is modeling and simulation, but we'll talk about in a minute. So after you have identified the key stakeholders who are participating in this project, then there's the project management. And you heard the announcement this morning, starting from June, pretty much every license of SolidWorks will have some shape or form of these collaboration tools. Project management is another key part. I know a lot of the companies either use some of the standard Gantt charts or Excel or whatever, but now in 3D Experience Works portfolio, you actually get very nice suite of products for managing your product, going from design to improving the design to delivering it to the shop floor. I don't know if this guy stopped working. Let me check. looks like this video is not working, so I'm going to skip. But basically, in this video, we actually showed a nice dashboard that was used by the stakeholders to interact with each other, agree on the requirements, and then start with a SolidWorks CAD saying, okay, these are the designs we need to improve. And then we come to the heart of ModSim, which is SolidWorks as a CAD engine working very closely with simulation solutions that are on the platform. What do you mean by working closely? If you make a design change in SolidWorks, you need to automatically update the simulation model on the platform. That's the kind of interoperability we are talking about, so that you can explore as many variants, as many changes, and the impact on the performance sort of on the fly. So we have solutions for different types of performance analysis. For strength and durability, we have Abacus-based structural solvers, which are extremely powerful. Abacus is a market-leading technology for structural simulations. Then for fluids, mainly in this case, could be HVAC performance if you're designing pumps or impellers, that kind of internal flows, and then as well as thermal problems. So in this case, we're going to show a case that involves cabin thermal comfort for an operator. Right? So we do have a technology for computational fluid dynamics that's embedded in the platform. Then comes injection molding. If you have plastic parts that are injection molded, you don't have to wait till your supplier provides the part. You can analyze or do some very simple and basic analysis of plastic fill to make sure that you're not making any fundamental mistakes, that you have to wait for your supplier to come back and tell you, saying that, hey, this part is not manufacturable or it's going to have these many defects. You can do some really easy upfront simulations of these plastic parts and provide a design that's less likely to fail when it comes to manufacturing. And last but not the least is the antenna design, placement, and assessing if this antenna is going to interfere with other electronic communication devices within the vicinity, because that's the most important part in electromagnetics. For some reason, I keep messing this up. So we'll start about talking about how SolidWorks customer or SolidWorks user can launch 3D Experience platform directly from your UI. So first and foremost, you have your SolidWorks CAD in X number of configurations, and you can directly save this model on the cloud with 3D Experience platform. And last but not the least, you can access this data, access this information from any device and from anywhere. So you have a core designer who has the designer license, who has the model, and then anybody within your team who wants to just look at the design, they don't need to have the designer license. You can share with them this model in a view-only mode from their browser. So they could log in, they just have to create a login, review the model, provide feedback. That's the social collaboration part of it. And then come back to you saying, hey, can you make these changes? It could be your engineering manager, or it could be a teammate from a different domain. So in this example, we'll basically look at how SolidWorks CAD goes to 3D Experience platform. I'm gonna exit real quick. I'm not seeing any of the videos being played, sorry. All right, looks like it's playing in this mode. That's okay. So we are launching SolidWorks from the browser using this application called SolidWorks connected. And once you're in the UI, you're bringing your model, so which in this case is the boom of the device, and then you're saving this device on cloud, and it's interoperable, meaning if you make a design change to your configuration, that can be automatically updated on cloud. So once you have this design up on the 3D Experience platform, you can launch any of the simulation capabilities. So in this case, we're going to do a structural simulation of the boom to identify the strength and improve the same. So the UI that you're seeing right now is of 3D Experience platform, where we'll start performing the boom analysis to start with. And if there's any design change that happens in SolidWorks, that could automatically be updated on the 3D Experience platform where you're performing these simulations. So that said, we'll go into the details of the simulation, but I just want to highlight some of the key user values that we're going to look at. First is this very tight integration between requirements, modeling and simulation, and there's traceability throughout the process. You can always look at how are these design changes influencing the top level requirements because they're in your feature tree, and you can do a quick pass or fail test. Then you have the user experience, which is very designer centric. So you have an assistant panel that will walk you through every single step of the model simulation setup. And that makes the life of a mechanical designer easy who has minimal to no experience in simulation. Then is the physics capability. So we talked about 5 requirements, right? Coming from structures, fluid, thermal, injection molding, and electromagnetic requirements. So good news is we do have technology to address all those requirements. And then is the cloud. That's quite important to keep in mind because simulations in general are computationally expensive. One of the challenges we've had with SolidWorks simulation or SolidWorks desktop is it's really good, really powerful, very easy to use. But as the size of the model increases, as the number of parts goes from 100 to 1000, then you start hitting the limits. Then there's a limitation also in terms of solver scalability, which seals around 12 or 16 cores. So if you want to do more, if you want to go after more challenging applications, then cloud becomes almost a necessity. So we are going to have this company called PES, which is a engineering consulting firm, tomorrow on stage. And you'll hear from this guy called Tyler Cook as how cloud actually helped them not only solve problems faster, but also go after more complex problems. So because of this, they are able to reduce the turnaround time quite significantly from days to hours. This means they're able to take up more number of jobs, take up more complex projects, right? And hence their business has a direct impact because of them taking advantage of cloud. Scalability is another very important aspect we'll talk about. This involves usage among various kinds of users. You don't have to be a simulation expert to leverage some of the simulation capability. And you don't have to wait until the product is in a mature stage to do these simulations. We've seen a lot of our enterprise customers, such as the Boeings, the JLRs, who start simulation right at the conceptual level so that when the product goes to bench test, the chance of failure is quite minimal. Last but not the least, a very airtight communication and collaboration between all the stakeholders is what you'll see during this process. That said, let's start with structures. So there are two use cases I'm going to talk about. The first one is this boom assembly, which is this arm and this bucket that you're seeing here. And we want to improve the strength. And we want to do this in a very concurrent fashion, meaning we want to make design changes in SolidWorks, but we want to leverage Abacus-based technology on the 3D Experience platform for structural simulation. Then we also want to ensure safety of the operator. So we'll talk about a rock impact analysis on the operator cabin. And this is not some made up stuff. So tomorrow you will hear from Resumen this actual case where they have a compliance and a regulatory requirement to pass the rock test, where they drop this, I don't know, 240 kilonewtons of rock on the operator cabin. And there's video that shows the actual test. Obviously, there's a dummy inside the operator. I don't think there's anybody in Resumen who's brave enough to sit inside that cabin. But there's also simulation playing side by side, and the simulation results look so close to reality, right? There's this myth that, hey, we can replace physical testing with simulation. I don't agree. You can reduce the number of physical tests with simulation. That's the right use, especially for industrial equipment design, right? Because you won't get that sense of confidence that you get in a physical test when it comes to simulation. All right, so starting with the structural application, we're going to talk about two different workflows. The first one is this linkage rod that's connecting the bucket with the arm. That's the one that tends to fail very often in the field because it's experiencing all these loads, these torsional loads, these linear loads, these rotational loads. So you not only need to improve the strength, but also the life of this linkage. Because if this linkage breaks, it's not the cost of the linkage, it's cost of the attachment, right? And there's also a liability. What if the bucket, falls on somebody's head? Then this company is screwed. So this is one of the top requirements. So to address this challenge, you can take advantage of this role on 3DEXPERIENCE platform called Durability and Mechanics Engineer. Some of you may be confused as to what role is. Role is equivalent of products. So on the 3DEXPERIENCE platform, we have basically customized products based on the user persona. Who's the user using this product? And we put a bunch of applications that helps the user address a certain type of workflow. So in this case, we're helping you address durability and structural mechanics requirements, right? So what are the highlights? The main thing is the durability solver. That's from a famous technology called FESafe. So FESafe is very extensively used in industrial equipment, automotive and aerospace industry. So we've taken that solver, taken the technology and integrated it into the platform. Then is the Abacus, which is quite popular in the industry for structural simulation. But most importantly, when the complexity of these assemblies gets crazier, there's general contacts. So if you have nonlinear simulations, then you have to deal with very complex contact scenarios. So we're known for quite robust contact options and also fastener, connector, and weld models, because you're not going to actually create CAD for these fasteners when it comes to simulation. Yes, you may have it in your bill of material, but for simulation, we do a lot of modeling, a lot of simplification, just from a practical standpoint. So we do offer a broad library of fasteners, connectors, and weld models for these kind of simulation. So let's go ahead and take a look at how this user interface looks like. So again, I'm launching the platform or launching SolidWorks directly from my browser because it's very well connected, and accessing the rod for performing durability analysis. And once the model opens up, so this is your SolidWorks UI that's being launched. So very first step is we create what we call as a finite element model, which includes the material, the meshing information, and then the parts that are participating. So there are some really powerful meshing tools beyond SolidWorks simulation that you can use. So in this case, we are using a hex mesh and do a quick quality check. And then that's it. You refer the coupling points for loading. And once these loading points or coupling points are set up, you're pretty much going to go in and define the loads, define the output monitors, and run the simulation. This entire geometry is tied to SolidWorks, so any design change that's made in SolidWorks will be reflected here. So I'm going to skip some portion of this so that we can get to the load cases. So we're applying the acting forces in different directions. We've defined the constraints, and then you can have as many load cases, and you can run them either serially or in parallel because you have access to cloud. Right? This is the point I actually want to quickly talk about. So one of the nice things about 3D Experience Works Cloud is if you want to not use cloud and just run it locally, if you do have, say 8, 16 number of cores, you can do that. The user has the flexibility to run these simulations either locally or leveraging cloud. And typically what we've seen with our customers is if they have access up to 8 or 12 cores, they just run the simulation on their desktops or their laptops. But if they want to go crazy, dealing with a more complex model, dealing with something that has 4 or 5 million degrees of freedom, then they take advantage of cloud. One of the new features that we introduced, which not a lot of people know about, is with your license, you do get up to 8 embedded cores of compute, meaning that you can either run those 8 cores locally on your machine, or you can run up to 8 cores on cloud at no cost, because your license comes with something called 8 embedded cores. The advantage is that on the cloud you get much better CPUs in most cases with much faster fan speeds. So the turnaround time seems to be better even for the same number of cores versus your local machine. Right? So you can run as many load cases as you want, and on our cloud we have up to 144 cores at your disposal. So depending on the turnaround time requirements, depending on the project requirements, you can pick and choose the compute capacity. So what we are looking at here are some of the results, including the stress profile, trying to find out if there are any key issues. And then the durability analysis is created off of the structural analysis to study the overall life. And you can even set up some really nice surface finishes. There's a library of different types of finish for the surface that you can consider in your durability analysis. And you can even combine test load history with the FEA analysis. I'm sure a lot of the companies have this loading history, has the shaker test data. So you can actually input the test data to run simulations that are close to reality and get a realistic prediction of the durability of the product. So here what we are going to look at is the overall life, or what we call as log of life plot for this particular model. And we're looking at any region that will not last around 1,000 cycles. So the minimum log of life we are seeing is about 2.5, which is not so bad for this particular analysis. So that's how relatively easy it is to set up a durability case in the 3D Experience platform once you've performed a structural analysis. The next one we are going to talk about is safety, right? So there are two use cases. There's the boom strength, which is the arm, and then there is the rollover protection system. So there's this role called structural mechanics engineer role, which brings you the Abacus-based technology for structural simulations. And the key advantages or the key values that are offered to our users is explicit analysis. Whenever you have some really crazy nonlinear simulations that may involve material nonlinearity, geometric nonlinearity, or contacts. I don't know if any of you have used SolidWorks Simulation Premium. When it comes to contacts, I remember those days when I would hit the run button in the evening, come back next morning, pray for 5 minutes, then open up the machine. You guys know the drill, right? But that's not the case anymore because Abacus has captured automotive and aerospace market for this kind of analysis, for nonlinear analysis. But now that's made available to SolidWorks users. So you can take advantage of the structural mechanics engineer role, which has very robust nonlinear explicit modeling capabilities. I'll show you how that looks like. All right, so again, the starting point is the SolidWorks model for this boom assembly, and we go on to the 3D Experience platform. So first we save it on the cloud, and then we launch the respective simulation role. So in this case, it is structural mechanics, and there's an application called mechanics scenario creation that walks you through the process of defining the analysis. So we created an analysis case kind of similar to project in SolidWorks simulation. So you can create as many abstraction shapes. So abstraction shapes don't exist in bill of material, but you are using them for simulation purposes. So we're going to create abstraction shape for rods. And the feature tree that you're seeing is deriving parts from SolidWorks. It's not adding anything new, but you can create abstraction shapes that stay only in platform so that your bill of material in SolidWorks is kind of unaffected. So here is the boom, and we basically go ahead and set up a structural simulation on this. So one of the nice things on the 3D Experience platform for structures is the surface meshing. It's really, really automated, really powerful, especially when you're dealing with mid-surface meshes. You don't have to do a lot of pre-processing to get them to work, right? Because typically mid-surfaces create gaps in T joints or L type of joints. That's taken care of automatically by the meshing tool. So here is the bucket where you're specifying the loads that are acting on it. And then we're showing the beam modeling capabilities. So it has quite a broad range of meshing tools, meshing capability, but the UI is quite simple. You have very few options to specify. Then we are showing the line fastener library that you have access to. So you can define all kinds of fasteners, specify the key parameters. If you're not sure, you can go with defaults. So we created the mid-surface mid-surface mesh for the entire geometry, and then beam mesh for some of them. And we are almost ready to go. So you have a quick quality check to make sure that there's no gaps or anything in the mesh. And then you can even couple with the solid meshes. So this is what I like about platform. You can have combination of solid shell beam meshes in the same model depending on the requirement. Because for some geometries, it may not make sense to model them as shell, right? So you can mix and match these types of meshes. But if you want to keep it simple, you can mesh the whole thing as a solid. Yes, your mesh size will go bigger, but you can take advantage of cloud to run them. So once you have this analysis case set up, we run this simulation for strength. And another cool feature that I really like is comparing plots side by side. So you're looking at the result comparison between baseline and modified design on the right hand side that has a slightly different cut for displacements. And you can do the same for stresses. So in here on the left hand side, you're seeing relatively higher stresses in the cutout region, not so much on the right hand side. Same thing with displacement. It's a lot lower displacement compared to the original design. So that's the structural capability. And I also wanted to talk about the explicit analysis, and rollover protection system is a great case because here you're trying to roll over the entire cabin and see how strong is the cabin in terms of its integrity. So again, you start off with abstraction shapes to add things that are more relevant to your simulation without disrupting your bill of material. So once these abstraction shapes are created, then we get into the meshing phase. So this is the top protecting cover, and that's being, and there we are defining a rigid, rigid body option. So I want to jump to this portion. So in terms of the explicit solver and the contact, it's pretty automated. You define, there's a general default contact algorithm that kind of takes care of most of the contacts, but you can override them if needed. You can specify all the parameters that you need to track. So in this case, it could be reaction forces that are acting on the system. And once you apply the prescribed loads, so in this case, we are applying a translational load at the top to mimic the rock falling or to mimic the rollover of this cabin. How hard is this in SolidWorks Simulation Premium? Very, very hard. So in 3D Experience platform, being able to get these kind of displacements, being able to see these kind of contacts is pretty easy. And it scales very well with cloud. So we've tested it across multiple cloud configurations, going from 8 to 16, 36, 72, 144. It scales pretty well, especially up to like 72 cores or something. So this is another really nice and powerful capability that's tied to SolidWorks CAD. So if you go back and make design changes to your roller cage, you just come back here and hit the simulate button, which is gonna remesh, rerun, unless you introduce a new part, because we don't have AI yet in this to say, oh, there's a new part. No. Okay, moving on. Let's talk about the comfort. Does any of you deal with HVAC systems? Yes? No? Okay. Then this will just be a fancy part of the presentation. So fluids, at least, is a critical part in most machine designs, right? Ensuring that it's thermally efficient. You may have air-cooled systems or liquid-cooled systems, or you may be dealing with some sort of a piping system, or in this case, we're going to talk about HVAC and human comfort. So we use an industry standard CFD solver under the hood, but it has a nice guided user interface, which provides step-by-step guidance to a non-CFD expert. You don't have to know anything about CFD, you just have to know the operational conditions of your system to be able to simulate flow or thermal performance. So that's what we're gonna take a look at using this product called Fluid Dynamics Engineer. So here I have a HVAC unit. So this is the HVAC unit that is facing the operator. So the black colored outlets, there are 6 of them. 2 for dealing with the windshield, 4 of them are the side vents, and then the bottom 2 are the foot vents to provide overall cooling or overall comfort. So one of the things you will see is not only design change, but you can do design exploration as well. So we start off with this guided user interface. So on the right hand side, so here we are just defining whether it's an internal flow, where are the outlets, where are the inlets. So once we have these defined, there are very simple step-by-step guidance. Let me pause. This is a super fast video. So this is something I wanted to quickly talk about. So meshing is a scary term for a lot of designers because the general understanding is you need to have a really good mesh to get really good results. But how do I know what is the starting point? So we have simplified it for you guys. There's a simple slider bar that's provided to users to go from, coarse to fine. And if you keep refining your mesh, you'll hit a point where the results no longer change. That's probably a good stopping point, right? Another very important aspect of this capability is this guided user interface. So right here, let me go back a frame. Yeah. Right here, what you see is an assistant panel that's providing red or green to a user on whether he or she has specified all the inputs needed to perform a simulation. Not only that, it's also giving you commands on what needs to be done next. Right? There's real-time feedback for a non-CFD user, non-fluid dynamics expert to set up the problem. Right? So using this, we are able to set up a HVAC analysis case that involves a evaporator and a heater in the middle, which is what we're specifying. And it has all these outlets that you're seeing. And in here is a blower that's actually blowing the air on the inside. So we are specifying the inlet condition at the blower, and then we are going to look at the pressure, or we're going to look at the flow rates on the outlets. So these are some of the parameters for the evaporator and the heater that we specified. And once you have set up the simulation, you would identify the outlet parameters. Typically, we look at things such as what is the percentage of airflow split at different registers. Ideally, you want them to be uniform. And also, depending on the mode, if it's a head mode or foot mode, you want to distribute the air accordingly. So there's also this automated body fitted meshing that's done behind the scene. The user doesn't have to spend any time on the meshing part. And once you run the simulation, you can do all kinds of visualizations on how the airflow is being distributed across these 6 or 8 different outlets. And once this baseline case is done, I'm going to go back to SolidWorks and make a design change because I'm seeing these blue regions in the pressure plot, which means there's air that's recirculating in that area, creating lesser efficiency. So in SolidWorks, we go in and make a change to the bend radius of those HVAC ducts. Now we update the same model on cloud. This is the beauty. You come in here and literally just hit the run button to update the FEM model and run the analysis. So now it's generating the new mesh, updating the simulation results, and you're going to see the new results. Right? This is the power of modeling ModSim, which is unified modeling and simulation. So we're going to save the results from baseline simulation case and then compare it with the modified. On the right side, you're not seeing that jump or that recirculation. But now we are going to go one step ahead and run a sweep of studies with various flow rates. Right? So you can do a design exploration. There's no limit that I'm aware of. I did a project for Lockheed Martin where we ran up to 3,500 design points. Right? These many simulations, just leveraging cloud. So you can set up the input variables and what are the output parameters that you want to track. And then you run the simulation and get a really nice response curve that allows you to make really important design decisions. So here we are setting up objectives, which is do we want to maximize a certain value or minimize a certain value for each of those ducts. Once this setup is complete, I'm going to go ahead and run the analysis. And what you're seeing on the left-hand side is information related to various variants. So we look at minimizing the pressure at the outlet that gives maximum flow efficiency. And we also need to ensure that mass is conserved, which is mass going in should be same as mass going out. So once you have these hundreds of simulations, you can actually even rank them on which design is better compared to the other based on the output parameters. Somewhere like this. All right. So that said, let's move on. I want to talk about the cabin comfort aspect of it. So now we have completed a HVAC analysis. We have done several variants of HVAC to identify the best design, to identify it's going to perform okay in all scenarios. We take that as the input boundary condition and set up an operator cabin. So again, we are taking advantage of this assistant panel that's providing step-by-step guidance to set up a model that involves the entire cabin and the human. So we are simulating solar radiation. We are simulating the heat that already exists in the cabin when this vehicle is parked in the sun for hours together. And what we're trying to figure out is how long does it take for the cabin to reach an optimal temperature that's set by the operator. So I'm going to skip some of these parts in the interest of time, but you can get into a lot of details. So here we were studying, the temperature variation at the chest, at the arms, on the forehead, and so on. So I'll go to the results part. There you go. So what we found here, I think in this case, was that the maximum temperature, which started at 55 degrees inside, it would take about 3 minutes or so for the cabin to cool down. That's a very important piece of information. There you go. So on the x-axis is the time, on the y-axis is the temperature, and we figured that within about 180 seconds, it reaches a constant temperature that's set by the user. So that's the thermal comfort aspect of the ModSim workflow. Moving on, plastic injection. I know this is one of the key aspects when we talk about design. And as I mentioned earlier, you don't have to be a plastics expert. You can be a mechanical designer, but still perform some basic plastic part filling simulation that can eliminate the back and forth between you and your plastic supplier or manufacturer. So in this case, we're going to look at the back seat, and we're going to look at it not only from injection molding perspective, but also from safety perspective. So in some of these cases where you have an open cabin, there are chances that a piece of rock might hit the seat, right? So you need to ensure that it's not only manufacturable, but it's also strong enough to withhold or withstand those loads. So we'll run a plastic simulation, and then we'll couple it with a structural simulation that's going to experience this load. So this is done using the same solver technology that exists in SolidWorks Plastics. It's called Simpo. It came through an acquisition of DS many years ago. They're actually based in Taiwan. And this offers end-to-end injection plastic molding capability, from filling to packing to cooling to warpage. One of the nice things about this particular role called plastic injection engineer is you can map the fiber orientation that's coming out of this plastic simulation onto the structural role for doing a structural impact simulation. All right, let's go ahead and take a quick look at this. So here is the initial or the baseline seat design. And we're going to start setting up the plastic simulation, and you will notice how simple the user interface is for a non plastics expert. So on the right hand side, you have the same assistant panel that's asking you to select the parts, the materials, the process, the conditions, and then simulate. So here we select this entire panel on the back seat and we specify injection location. There's also an auto injection which will automatically predict the gate locations if you want based on the geometry. So here we are going to inject plastic from the back of the seat based on somebody's experience. And then you can take advantage of cloud for running the same simulation. So once you have the simulation complete, you can visualize fill time to make sure that the whole part is able to fill comfortably. You can check for warpage, right, which is quite important in this case. You can check for failures and also fiber orientation, which then gets mapped to a structural analysis case. So here we are simulating the impact of rock on the back seat, and it's also part of a certification or compliant process. So under material properties, you would basically bring in the fiber orientation from your plastic simulation and then set up the structural simulation as you would in any other scenario. So if I look at the result from the impact simulation, the stresses just in that corner are pretty high. So now we go back and make a design change. We're going to introduce more number of ribs, check if that's going to impact the injection molding process. So here are the ribs that are added. And when we go back to the plastic injection simulation, we don't have to set up the whole process again. It's already set up for you. You basically update the simulation and hit the run button. So we compare the fill times. Obviously, the one that has ribs will have longer fill time because it has more cavities to fill. But as long as there are no key issues such as knit lines or air traps or shorts, you should be okay. And then we see that the wrap or the warpage is reduced from 5.27 millimeters to 4.5 millimeter. And the maximum stress is within the acceptable limit of 70 to the 8 Newton per meter square. So this is the multi-physics aspect of platform because all the capabilities are within one single user interface. Okay, so we looked at the structural capabilities, flow and thermal capabilities. Now we're going to address the requirement associated with electromagnetics. So electromagnetics has always been kind of new or alien to a lot of mechanical designers. I come from mechanical background and I still struggle with electromagnetics, to be very honest. But I have some smart colleagues in that department who help me out. What we are noticing is that a lot of the industrial equipment customers are converting their existing machinery into IoT. They want their devices to be smart. It's not that they're redesigning their devices, but they're considering strategies of putting the right antenna in place so that they can get real-time feed of their devices. So one such instance here is we want to place an antenna on this bee excavator so that we can track the positioning. It's a GPS antenna that we are placing. And there are two workflows involved. First is identifying the right location to place the antenna, which will have minimal obstructions in terms of communication. Second is what we call as co-site interference. So co-site interference in very simple terms mean if you have multiple antennas, multiple sensors, multiple communication devices, you need to make sure that they don't interfere with each other. Right? You need to make sure that they're somewhat efficient despite the presence of all these devices within the vicinity. So we're going to take a look at this role called electromagnetics engineer role. This comes from the industry leading EMAG simulation technology called CST. So CST started out of a university in Darmstadt, Germany, and they're really known for their antenna libraries, antenna design solution. And DS acquired them in 2016, 2017 timeframe. So we have integrated this technology onto the cloud solution, and it's not only about providing electromagnetic simulation solutions, they also offer a broad range of antenna libraries that a mechanical designer can explore. Meaning, you don't have to create antennas from scratch. You can say that, hey, I'm interested in putting a GPS on this thing. Show me the list of GPS antennas you have in place. And they usually update these libraries once every year or once every 2 years so that they are aligned with the latest offered by the vendors. There's also very powerful PCB modeling capabilities. I don't know if you guys deal with any electronics or PCBs, but they can handle signal integrity, power integrity, and thermal modeling of PCBs if needed. So in this case, we start off with a baseline design or baseline location for the antenna. It's so weird having to do this every single time. So ideally, we would like to place the antenna on this back cover, which is not, or first, we actually ran a thermal simulation to find out which portion of this back panel is not so hot. And we decided to place it, I'll show you in a bit. So this is the electromagnetics engineer role, and what you're seeing is the placement of the antenna a few centimeters behind the exhaust, and the exhaust is pointed in the outward direction. So that's kind of a safe location for the antenna. So what you're seeing on the right-hand corner, which just disappeared, is a library of antennas. So you can run your simulation on the platform, you can post-process the result on the platform. So this is using cloud, as you can see, and once we run these simulations, we are going to look at various parameters. One such parameter is called S parameter. I'm going to talk about it in a minute. So far field is a plot. Actually, let me go back. This is going super fast. Yeah. Far field is one of the key parameters that we look at from an electromagnetic standpoint. In very simple terms, you want all this thing to be red. It just means the directionality of the antenna. It's able to communicate without any obstructions. You are seeing green here because obviously the signal cannot go around the corner. As long as majority of this blob you're seeing is in red, that means your design is, the location is okay. So that's the far field plot. Then there's another plot that you're going to see called electromagnetic distribution that ensures that there's nothing interfering in between. So we changed, that was our starting location, and then we said, okay, why don't we move it to the top, from the back to the top, and see if there was any change in the directionality and directivity of the antenna. So we go back and just rerun the same simulation or the same setup with the new geometry in place. And once you have the new simulation, you can actually compare them side by side. So you see much better coverage in the second case compared to the first one. This is the, actually let me go back. Yeah, right here. Yeah, there you go. So this is a very good visually appealing tool that gives you a sense of whether your antenna is able to, gain maximum far field from a particular location, right? These are the simple simulations that you could perform even without electromagnetics background. It took me some time to understand this as a mechanical engineer myself, but now I get it. I may not get all parts of the physics, but this is a good starting point for you to consider if you're thinking of IoT. We are almost at the edge of the hour, so I'm going to wrap up in a minute. But basically, once you do these kind of comparisons, then you can place multiple other devices and run what we call as co-site interference, which is these sensors, these devices, not interfering with each other. So these were some design changes we made. We also added 2 of these bars to protect the antenna in case there's a rock that comes and hits the top, or in case there's a rollover. So these were, this is done to show that the overall model is so well connected to simulation that we didn't have to actually spend a whole lot of time updating the simulation model. So there are 2 of this, and then we go back and rerun the simulation just to make sure that these bars are not creating any interference. Yeah. So now the model is set up. You pretty much go ahead and rerun the same from the 3D Experience platform. And then you look at the results, the far field comparison between them. Right. And this is the library I was referring to. It's called as Antenna Magoos. So you don't have to build new antennas or know anything about antennas. You just have to access this library and say, I'm going to start with this one and try to explore. All right, that said, we're going to go ahead and wrap up. I just want to summarize that using this ModSim approach, where we are tightly integrating requirements, collaboration, modeling, and simulation, we can address all these kinds of requirements that come up in a typical industrial equipment scenario. I mean, this was just an example for you to get a sense of what are the capabilities that we have to offer. But at the end, this whole assembly, when we did this project, it's not 5 different assemblies that were used for this simulation. We just used one assembly, but there were several people from different parts of the globe. In fact, we did this during COVID. So the entire collaboration actually happened on the platform when we completed this work during last year. So to summarize, what are the engineering values? What does it mean to you guys, right? It's fully integrated because of the digital continuity. You have very powerful physics, so the data you're getting is based out of physics simulation. Tight integration between multiple disciplines. You saw that in case of strength to durability, fiber orientation to structural simulation, and so on. They're tightly coupled. And collaboration between external and internal stakeholders. And lastly, the cloud compute, which is a pretty big differentiator. From a business standpoint, it's quite straightforward, right? This is going to help you accelerate time to market by using simulation as much as you can to minimize prototyping or testing, and innovating broader portfolio, right? Being able to test various types of scenarios, various types of variants, and going back and forth between SolidWorks and platform for design and simulation, and operational efficiency in general from a productivity standpoint. And last but not the least, the IT costs, which are pretty heavy for a simulation infrastructure. You don't need a bigger machine. You're always up to date on the version because cloud pushes those versions automatically. And then it's pretty secure, so you don't have to lose the data or think about data losses. Okay, that's all I have. I hope this was useful to everybody.